now move to our topic 11, chance. Okay, so now you will start to see that, oh, let me share my screen. Now you will start to see that why we are interested in talking about those different conditionals comparison for now, okay? Because you will see that later for all of the inference that we are talking about in this course, we're trying to do what we call like a simulation based inference. Okay, we're actually going to try to simulate just like the game that we're talking about. We want to simulate games, and then maybe you'll be wondering, okay, whether this is a fair, like maybe you'll be wondering, like say, whether this is a fair six-sided die, okay? And then one way you can do is you can simulate like a large number of experiments, okay, and then check against maybe some of you know about like say null hypothesis or Turner hypothesis, things like that. And we're gonna cover that in detail as well. But just so you know, all of the conditional statements, the comparison that we're covering just now is gonna be very important in understanding how we can create a simulation-based inference, okay? Because all of them are building blocks of how to simulate games, and then of course, simulate the game for a large number of times and see whether it makes sense, okay? So to get us started, okay, we're gonna first talk about the random selection, okay? And what we mean by random selection is, well, let's just say the example, like the demo that we did earlier about the simulation of the game, if you remember, we only did part of it, okay? So let me bring us back really quick. Yeah, so if you remember the game, we're saying that if it comes up 1 or 2, or 3 or 4, and 5 or 6, right? The function that we're writing earlier with the conditional statements is only after I already know what the die is going to come up with, okay? Like remember, that's what the row that we're passing into the function that we're writing, okay? But now for us, the next question is, if I really want to simulate the game, I also need the piece to actually roll the die, okay? And I know it's a six-sided die, okay? So the missing piece, which is the one that we're going to talk about, is how to actually create or randomly select, in this case, out of the 6 possible values, okay? So that's what we mean by random selection, okay? And then in Python, pretty straightforward, okay? You have this NP, so it's in the NumPy function, NumPy library here, np.random.choice, okay? It's gonna select, read it carefully, select uniformly at random with replacement from an array of a specified number of times, okay? So put that, I guess, into an easier to understand notion. We are providing, okay, an array of choices, okay? And then once we do this np.random.choice, we're selecting uniformly at random with replacement. Okay, so what that means is that if I'm supplying the array of 1, 2, 3, 4, 5, 6, okay, what this np.random.choice being used on top of that array, like as the input, what we are doing is that we're randomly selecting, okay, one of the 6 values, okay? And then once I'm done with this, if I do another one, it's gonna randomly select from 1 to 6 again, okay? So that's what we mean by with replacement, okay? When you select one, okay, you are saying that, well, I'm only selecting one of them. But if you start to do 2, then what we mean by that is that you can get 1, 1, okay? Because when you select the first one, you still put it back. And then again, it's gonna be a uniform random selection over there, okay? So as you can see, there are multiple arguments. You can go with multiple arguments. The first one has to be the array that we're selecting from, okay? Again, it's uniformly at random, so it's equally likely all of the outcomes. And then the sample size is actually the number of selections that you want to do over here. Okay, so you can have this additional input argument over there, so you're able to do that. Okay, so let me go to the demo. So we'll see how that can be done in practice. Okay. Okay. All right, so most commonly later in the semester, you will see that a lot of times the random selection we're doing is especially trying to work out, if you remember about our causality statement, how you can make causality statement, we're putting people in the treatment group and the control group, right? And then we're trying to do a randomized experiment over there. So a lot of times, maybe the choices that you're making right now is between treatment and control. Okay, so this is the first example that we're having over here. Okay, so experiment groups, okay, it's an array of treatment or control. Okay, you can imagine that later on when we know how to do it for a large number of times, we're doing this kind of assignment, right? The group assignment for each of the observation. Okay, all right, but to get us started, to get there, we first of all, okay, decide the experiment underscore groups. That's the array of treatment and control. Okay, so remember the np.random.choice method you will have to supply the array of the outcomes that you're interested in. Okay, so we create that and we name it as experiment underscore groups. Okay, so now I'm going to do one random draw. Okay, it turns out to be treatment. Okay, and then I can do another one. Well, turns out to be control. I can do another one, it's control, and I can just keep doing that. Every time it's a random chance, okay? It's a random draw, I should say, and it's equally likely. It could be treatment, it could be control, okay? So just all of the default, like you can see here that we don't have the second input argument, right? Because the default is 1, we're only making 1 random draws, but we can do 10. Let's just say we do 10, and then you're gonna see an array, okay, of the outcome. Each of them is one of the outcomes over here, treatment, control, treatment, etc., etc. Okay, and then it's an array. So now hopefully you're so familiar with this now that whenever we do an array, we might want to do some kind of arithmetic about it. Okay, so first of all, what if I want to do sum of the, like I do 10 choices, I do 10 random selections, and then I want to know how many of them are control. Okay, so when you do that, well, you can use the sum method and then equal control. Okay, so this goes back to what we just did the demo for the comparison of array, I guess, of the previous topic just now, and then we can do that. Okay, so in this case we have 6. Okay, and then in this case we have 6 again. Okay, so you might find it, well, if I'm only doing 10, how come I'm going to have 6 controls and 6 treatment? Okay, great question. If you have that in mind. Just notice every time we run the np.random.choice, it's a new set of selection. Okay, that's why this particular one, the one that we did over here, is different from this one. That's why we can have both 6. Okay, but if you only want to do it one time, then the general approach over there is that you're going to do this selection, right? And you call it something, so later on you can work on the particular one over here. So for example, if I name it selection, then if I do sum of selection equal control, and then I do another, I do another one called sum selection equal treatment. Okay, if I do that, then I'm pretty sure they're gonna sum up to, well, happens to be 5, 5, but they're going to sum up to 10 because we're doing the arithmetic or the Boolean operation and then checking the sum on the same set of 10 outcomes. Okay, so every time you run the np.random.choice, it's going to be a new set. Okay, that's why you might see something seemingly contradictory. But if you want to make sure that everything works out well, you might want to assign it to an object. So later you can operate on that object, which is fixed. Okay. All right, so well, I think that's exactly what I did down here anyway. So so that's what we mean by you can actually simulate, right? You can simulate random draws over here by using the np.random.choice method, okay? Make sure that you always supply the array of the outcomes, okay? But then of course, the second optional input will be the number of selections that you want to make, okay? All right, so with all that in mind, let's see how we can make that game working in the way that we hope it's going to work. Okay, so like I said, just to come back here really quickly, the one row function that we wrote earlier is only doing this part. Okay, it's only doing the part that is checking the 3 different conditions and returning you the outcome. Okay, and what we are saying here is that if we want to actually completely simulate this game, we also need to roll the die. Okay, and that's what we just covered. Okay, you can use the np.random.choice method to do a random draw. And let's see how that can be placed together to make this game complete. Okay, so the one that we're doing over here is like the die faces. Okay, I'm doing at np.a range 1 to 7. Okay, because we have 1, 2, 3, 4, 5, 6 different 6 different options. So if I do that, we know that it's going to be an array of 1 through 6. Okay, and then if I do an np.random choice on top of this, well, we know that we're just equally likely selecting one of the 6 options. Okay, so if I do another one, okay, I might get 1. As you can see, I do another one is 6, etc., etc. Okay, so that you can see that it's going to be a random process. And let me quickly, okay, yeah, never mind, chat, I got it. Don't worry.
Thank you.
Alrighty, so now let's see how to make the entire game complete. Okay, this is copied from before. If you remember, we have this one round function. Okay, the input is the row. Okay, so we know that, that's good. And now I'm writing a new function wrapping up this one round function. Okay, I call it simulate underscore one underscore row. Okay, actually, I don't even need any input. Okay, because the reason is the way that I'm doing it is that in this new simulate one row function, I'm gonna, first of all, you can see, take a random draw, right, from 1 through 6. And then second, I'm using the one round function that I wrote earlier to determine what is the output gonna be. Okay, so this is a function, as you can see, that doesn't need to take any input because we're really just simulating. We don't, like, there's no, I guess in this case, you can think of as, oh, I don't need any input to make it happen or make it run. So I can put it as a blank right now. Okay. And then for us, notice that this is a nested version over here, right? We are using the one round function, which is we wrote before, of determining, once I know the row, right, determining the output. However, just like what we talk about, we also need to have the rolling process going on. And we learned that the np.random.choice method can make that happen. So this function, once we run it, we can actually start simulating the game like what we're talking about. Okay, so the simulation has two parts, right? The first one is that we have to determine which ones, or like what is the row, and the rolling is from the random draw, like what we did. And then the second part is evaluating it based on the 3 if statements, right? And then determine the output. Alrighty, so let me try to run this. Okay, so this case is, I guess it's, the row is probably 3 or 4, right? So we have a 0 output over here. Okay, I do another one, it's -1. So I guess for that particular row, it's going to be 5 or 6. Okay, and you can keep doing that, just like what we showed before. Every time it's a new draw. Mostly because, as you can see, because the function, the simulate one row function, involves the np.random.choice, and we know that every time you rerun it, it's going to be most likely a different outcome. Okay, make sense? Make sense? All right, so if I come back here, yeah, just to wrap up really quick over here, the method function, the method name is np.random.choice. Okay, you need to have the first input as the array that you're selecting from, and the second is optional. Default is 1, but you can always make it larger if you want multiple outcomes or multiple rounds being done. All right, let me make sure. Okay, all right, so with that covered, we are ready to talk about, well, what if I want to perform my game for a large number of times? Okay, I want to see like how once I do a larger number of times, whether I can have any kind of general statement, or like if I have any kind of checking about whether the row is a fair row, stuff like that. Then what we needed is that, well, I run it for once, okay, and then I proceed to run the next time. And I want to make sure that I can cancate or like connect or like link all of the outcomes that we're getting into what we call like a new array that later on we can do summarize, any kind of summary about. Okay, so what we mean by this, we call it appending arrays, but pretty much if you look at what we're trying to do is that we're using the np.append method. Okay, what we're doing, the first one to use, the first version of using it is that if I have an existing array 1, I want to add a value, a new value to it. Okay, so we can do the np.append and then array 1 and then value. Those are the 2 inputs. So we are just adding a new value appended to array 1. Okay, caveat, and I think we probably know this by heart by now, is that the array, all of the elements should have the same data type. Okay, so if you are doing an array of integers earlier, the appended value, the newly appended value should be another integer, otherwise you're going to get an error message. Okay, so what this is doing, and later on you're going to see, is that, well, if I want to do this experiment one at a time, okay, but I want to do a large number of times, and I do, let's just say I do 10 already, and I want to do another one. Okay, what we can do is that, well, I have the array of the array 1 of the 10 outcomes from the first 10 experiments, and now I do a new experiment, and then the value of the new experiment, I want to append it to the original. Okay, so the append is trying to help us do what we mean by longer array, because I want to record all of the outcomes one by one. Okay, so that's the first way to use it. You can also do append of two arrays. Okay, so like say array 1, array 2, and then it's just the array 2. The second one gonna be appended to the first one, array 1, and then again, all of the elements need to be in the same data type. Otherwise, you're gonna get an error message. Okay, so keep that in mind. The purpose of doing this, we're trying to see that if we're able to do a large number of experiments and I want to do it like say one at a time or a few at a time, but in the end I want to collect all of the results together into an array, and that's the way that you can go about it. Okay, so let me show you some quick demos and then we go back again to the rolling game. Okay, all right, so the first array I'm doing over here is mp.arange 4. Okay, so that's going to be 0, 1, 2, 3, right? And the second one is going to be 10 through 16. Okay, all right, so the first demonstration, okay, is that if I do mp.append first and then 6, so remember whatever first is what I did over here, right? 0 to 3, okay, and I'm adding a new value into it. Okay, and you will see that, well, right, we have 1 through 3 first, and then we add that 6 over to it. Okay, so that's what this append is doing. But of course, if we just go back to first again, it doesn't change. Okay, if you want to save this, just like what we know by now, you want to save this to assign it to an object so later on we can access it. Okay, similarly, if I do the mp.append of first and second, okay, we're going to have a longer array of the two appended together, but the original two were never touched. Okay, so those are good things to keep in mind, and I think we have seen so many different examples by now. As long as you do any kind of operation, anything on any object, if you want to use it later, you always wanted to assign it to an object later so you're able to use it. Otherwise, like what we have seen again and again, you're never going to touch the original objects if you don't assign it to anything new. Okay. All right, so let's come back to the repeated batting that we're talking about it here. Okay, what if I want to do the game for a large number of times? Okay, and every time I want to record my results. Okay, and then here we can say that, well, if we are redefining all of the like the die faces through 1 to 6, and then the two definition, like the two functions, one round and simulate one row. Okay, those are from before. Okay. So the way that you're able to actually save all of the results, if you're going to run it one by one, is that I can first of all start with the results array, which is empty. Okay, because I don't have anything yet. Okay, so I do an empty array. Okay, and now I will run my simulation once. Okay, and remember, once I run this, I will have the outcome of the 0 or -1 or +1, depending on the row that I'm doing. And then I can append it back to results. Okay, so if you focus on the right-hand side, okay, we're doing the mp.append. Results is whatever the results that we have so far, which is empty array at this point. And then we can simulate one row. We're doing the game, okay? We append it to the results, and then we assign it to results again. So this is the case that, well, in the end, I only really need to know the array of all of the results, so I can reuse the object name every time. Okay, because in the end, I only care about that. But of course, if you care about any intermediate ones, you can always name it differently. But for our demonstration, we're doing append back to results, and then we assign it as results again. Okay, so remember, let me run this one more time. Right now, results should be empty. So let me actually just run that. Okay, yeah, so it's empty. Okay, and now I'm going to run my first game. Okay, and I'm going to append the results to it, and then now you will see that because I only simulate the game once, right? I'm going to get one result, which is 1.0. Okay, and I can do another one, not surprisingly, because I'm appending it back to the results itself. I'm just adding one more result over here. Okay, of course, if I do another one, it's going to be the outcome going to be an array of 3 elements, right? Oops, I have to run it. So it turns out that the third one is also a +1. Okay, so appending arrays, maybe at first you think that why would we ever do it? Why do we want to add or like say append any new observations or new results to the original one? As you will see soon, like we just saw it, but then also, like I said, later in this course, we're going to see a lot of simulation-based inference where we try to repeat the experiment so many different times. And then the append method going to be super handy here, because every time I run a new result, I can append it back to the original that I had. So I can just keep growing my final results array that I can collect all of the results that I need. All right, if that sounds good, I think we can come to the control statements. All right, okay, so we talked a little bit earlier, right, about the conditional statements, okay? Conditional statements, like what we're talking about here, back there is all of the if statements that we're doing, okay? And it's conditioning on the expression, then we do certain action, okay? So, but conditional statements also falls into the bigger umbrella, what we call by control statements. Okay, so control, if you think about the term, okay, we're really trying to show you in a sense that those control statements are useful in a sense that we can check the condition, and then once we know the condition, we're going to control for it and then do all the tasks that we need to do. So what we mean by that, okay, this statement's going to control the sequence of computations that are performed in a program. Okay, conditional statement is one type, like the if statement. Okay, it's going to control exactly what's going to happen. And then the for, okay, so this is the new one that we're covering here. Okay, it's another keyword. Okay, we're going to begin a control statements. And the for statement, as you will see, is that it's going to perform a computation for every element in the list or in the array. Okay, we'll see an example soon, but just so you know, when we covered the if statement earlier, okay, we know that now we know that it's also a control statement. Okay, it is used to define functions that choose different behavior based on their arguments, just like the if else if that we did, like 1 or 2, 3 or 4, 5 or 6. Okay, so both of them is what we call by control statements. Okay, and we have seen how if can be done. Now we're going to do a demo about for. And then for, as you can see, is another very commonly used way that we're going to do our simulation-based inference. Okay, and I noticed because earlier during our discussion, some of you have experience with Java or other programming languages. Then the for loop, I'm pretty sure you have seen that over there, and that's what like the Python world that we're delving into too is trying to do as well. Okay, so for and if, both of them are control statements. And then they're going to control the sequence of computations going to be performed in the program. And for is doing it for every element. Okay. And then if is given the conditions being satisfied, you're going to execute certain tasks. Okay. So let me show you the demo. And then I think hopefully we can get through this before we're going to end today. Okay. All right. So the for statements. Okay. We're going to start with a few toy examples and then again go back to the rowing game that we started earlier. Okay, so here the for statement. Okay, so let's take a moment to understand this line of code a little bit more. So what we're doing here, as you can see, is for pet, okay, in the array of cat, dog, and rabbit, we're going to print I love my pet. Okay, whatever the pet is being asked to return over here. Okay, so any guesses of what the output gonna be looking like after I run this? Okay, so recall, let me come back here really quick. The purpose for is to perform a computation for every element in the list or the array. Okay, so here, for pet, okay, in this array, I'm gonna print I love my blah pet. Okay, so before running it, let's try to understand this line a little bit more. It's saying that for any pet, okay, in this array, so I'm going to do cat, right? I'm going to do dog, right? I'm going to do rabbit, okay? And then for each of them, I'm going to print I love my blah pet, okay? So what this is doing is that, well, if my pet is cat, if it's the first one, then I'm going to do I love my cat. Okay, now I'm going to move to the second one is the dog, right? And I will print I love my dog. And the last one is rabbit. So I'm going to print I love my rabbit. Okay, so when we run this, you will see that 3 different lines are printed based on the particular pet name that is being done. Okay, down here, we broke it down for you just to show that what the for statement is really doing. What we're doing here is like, we're gonna access the array one by one, right? Remember, the for statement is trying to perform the computation for each of the elements, okay? So what we have is that we have an array of 3 elements. All of them are strings, okay? All of them are like, each of them is the name or like the type of the pet that we have, okay? So pretty much this more complicated version of the code over here is replicating what the for statement is doing up there, okay? So pretty much I'm doing like, if it's cat, like I'm accessing my item 0, like the first item is cat, so I'm going to print it, the second and the third, okay? So if I run all of this, it's going to give me the same output as before, okay? So as you can see that the for statement, okay, is super useful if you want to perform the computation for each of the elements, okay? And for us, while the example is probably not so complicated yet, because we only have 3 elements in the array and you do it one by one. So, but what if you have 30 or 300, right? Like say you want to do certain things about it. So like writing it down in this way will be so much more tedious. Whereas over here, you can use a for statement to do everything for you. Okay. All right, so keep that in mind, how the for statement is being used and how, like what is it used for. And now if we come back to our old example, okay, of rolling the die game. Okay, so we have the die faces, we have the one round function, we have the simulate one round function. Okay, all right. Now let's suppose I want to run it 5 times. Okay, I want to run the game 5 times. And just like what we did before, if we remember this one, okay, this was the previous demo, okay? If I want to run it 5 times, of course, I can just do this 5 times, right? Like I do like the np.append, results of a new run, I repeat this 5 times, right? And then I will get array of 5, okay, of 5 elements. But now we know the for statement, okay? Now we know the for statement, what this is gonna do, okay, can help us is that instead of repeating that for 5 different times, okay, I can write it in a for loop. Okay, what we mean by for loop or for statement, for statement over here. Okay, so we start with the game outcomes. Again, it's an empty array. Okay, and then we're saying that, well, we're gonna repeat this game for 5 times. What we do is like I stands for iteration. Okay, it's a very commonly used notation here. Okay, I'm gonna repeat this for 5 times. So I'm doing for, okay, I in 0, 1, 2, 3, 4. Okay, 5 times. Okay, so every time I'm gonna do a new row, right? I'm gonna append it to my game outcomes. Okay, I'm gonna assign my game outcomes to the new one. And then once I run this few lines together, I should be able to get a game outcomes of 5 outcomes. Okay, so let's see if we do get that. Okay, so instead of running it one by one and then you have new cells for each, okay, you can do it as a for loop. Okay, so the game's outcomes, we have -1, -1, 0, -1, 1. Okay, all right. More commonly, I guess, you wanted to repeat this game for a large number of times, and this is where the for statement can be super handy. Here I'm demonstrating doing the game for 5,000 times. Okay, it's gonna take a while to run, so let me run it for now. Oh, it's quick. Anyway, it is pretty quick. So 5,000 times, pretty quick. Okay, and let's just double check that we do get the number right. Like say the game outcomes, because we have run the game so 5,000 times, the length of it should be 5,000. Okay, so this is a sanity check to make sure that we have done it right. Okay, and let's see if now, because remember there are only 3 possible outcomes, right? -1, 0, and +1. So right now I could be like visualizing the outcome. I want to see like whether they're all equally likely, meaning that whether like say the die is fair. We know it's fair because we're doing the np.random.choice. Remember, it's uniformly equally likely, but still you might be wondering. So like if we do create a table of the net gain, okay, we know it's either 0, -1, or +1. Okay, and then finally we can do a bar graph. Okay, remember our bar graph friend, okay, over here. They're very similar, not exactly the same, okay, but very similar. Okay, they're like similar, like the number of occurrences, like the count over here, because we know that's going to be roughly 5,000 divided by 3 for the 3 different outcomes. Okay, make sense? Yeah, so the for loop or for statement, the control statement that we're doing, is super handy if we want to repeat experiment for a large number of times. Okay, but then of course, to make that happen, we need to know how to do the append, right? And then of course, we also need to have a readily available function to do the experiment itself. So in order to make that happen, as you can see that we build it up gradually, right? We talked about how to write if statements, right? Checking those conditions and then do certain execution. And then we talk about how to do like a random draw, okay? All of those two together come up to give us the experiment, like simulating one experiment, okay? And then beyond that, we talked about, well, if I wanted to repeat the experiment large number of times, then the for statement can be really useful, okay? All right, so I think given three remaining minutes, I should be able to do one more demo for you all. Let's do another experiment, okay? Let's simulate the number of heads in 10 tosses, in 100 tosses, okay? What we mean by that is that now instead of working with roll, rolling a die, we can flip a coin, okay? And the coin, of course, the outcome is either heads or tails, okay? So we're gonna make the array first. That's the outcome array. Remember, we always need that to do the np.random.choice. We always need the array, okay? So once I do that, okay, let's do the np.random.choice. Okay, what I'm showing over here is that what if I run it for 100 times, okay? And I want to check how many heads are out there. So, well, it's a fair coin because we know it's equally likely of getting the heads and tails using the np.random.choice method. So this outcome should be close to 50. Not exactly, but close to 50 if it's a rare, fair coin, okay? Alrighty, so of course, what we mean by like say this particular outcome is 55 and it's relatively close to 50, and that's just one experiment, okay? What we mean by like the multiple experiments right now is that what if I can repeat this 100 tosses a large number of times? I want to see how many heads each time is turning up, okay? And then the way to do it, okay, as you could imagine is that, well, we put this num heads, okay, into a function, okay, that's repeating what we're doing the sum over here, okay? And then I decided to do it for 10,000 times. Okay, so I need to run this now because I think this one does take a little bit longer time to do. No, it's done anyway. And so what this is doing, so just to sort it out clearly, where each experiment is doing 100 tosses and counting the heads, okay? And then each experiment like this, we're repeating it for a large number of times, like 1,000 times, 10,000 times, okay? And I want to see the number of heads coming out of this 10,000 different simulations. Okay, so I save everything into outcomes. Okay, and remember that's the outcome. The outcomes is storing the number of heads out of each experiment. Okay, so just like before, okay, we can put it into a data table and then do some kind of visualization. So let me do that for you. Okay. And you can see here, okay, we're doing a histogram, okay, because here what we're doing, we are the heads, right? Like heads, the number of heads is a numerical variable. So that's why we're doing a histogram, okay? And then what's interesting, and I think we'll see occurring similar shape of distribution a lot of times later on in this semester as well, is that, well, we can see that for a fair coin, right? And the number of heads out of 100 tosses, if I do this a large number of times, I can roughly see that the number of heads that's turning up is centered around the 50 value that we thought it's going to be, right? But sometimes you can get something as low as 35, right? Sometimes you can get something as large as 65, okay? And you can sort of get all kinds of values in between, okay? But then the general shape is, well, it's most likely, right, to get 50 because that's where it's centered and sort of like the highest, right? If you remember the height, right? Height of the histogram, because they're equal beams over here. So this is telling us, like say the height itself is telling us the frequency to some degree, right? So it's most likely at the middle, 50, but then gradually die down, okay? And then for so extreme values like 30 and 70 out of 10,000 simulations, we never saw any, okay? So hopefully this gives you an overview, and you can see that if some of you have taken any kind of like a statistics courses in the past, you will know that this is related to what we call like a normal distribution. And we're going to cover that later in the semester as well. Okay. But I want to use this example to show you all that this is what we mean by simulation-based inference. Okay. We're trying to repeat experiment for a large number of times, okay, and then see how we can make inference based on it. in the past, maybe your experience with statistics is that you have to memorize the memorize the formula and then doing the hypothesis testing following those formula. But now this course, we're trying to empower you to use computation-based inference, okay, is what we call by simulation-based inference, that you're able to repeat experiment a large number of times and then go about your inference from there. Okay. Yeah. All right. So sorry for the delay. I think already 2 minutes late, like overtime. So feel free to log off and.
Okay. So where we left off last time, where we started talking about conditionals and a good way to kind of see all of that together is we're going to talk about the Monty Hall problem. And so the Monty Hall problem comes from a game show back in the 60s and 70s. And the host of it was Let's Make a Deal was the game show. And the host was Monty Hall. And actually, you know, as everything old becomes new again, it's actually they brought back, you know, Let's Make a Deal. I think Wayne Brady is like the host of it now, but used to be this guy Monty Hall, and one of the kind of the more famous. And so this was where all of the audience would dress up in kind of crazy costumes, and then the host Monty Hall will just like pick members of the audience for just kind of random games. And one of the more famous games was this game where they brought the contestants up and they were shown 3 doors. All the doors were closed. And one of them would have a good prize, like a car, like something, you know, substantial. And the other 2 would have not a good prize. Often they actually would have like a live goat, all right? And so kind of the problem as it's formulated, you're presented 3 doors. One of them has a car, 2 of the doors have goats. And so the host will ask you to pick, you'll pick a door, one of the 3 doors, and then that's your pick. And then what the host would do is the host would open up one of the doors that you didn't pick. Okay, so if you picked door 1, for example, the host would then open up one of the doors that you didn't pick. In this case, 3, and they would always show you a goat. They would always open. They would never open like. They would always show you one of the losing doors. Okay, and then you were faced with a dilemma. You were given a choice. Do you either stick with your original pick? In this example, you stick with pick 1, or do you switch? Do you switch your pick? And in this case, pick door 2, okay? And so we'll work through kind of like empirically what is going on, and we can kind of figure that out with probabilities. But this was very controversial at the time, and people wrote columns about it, and people, you know, it turned into like flame wars and all of that. So we'll work through kind of the probabilities, which will be a good segue in kind of our next topic. But then we'll actually run a simulation. We'll actually just run, you know, play, you know, thousands of versions of the game and see what happens from there. But the upshot is, it is always better to switch. It is always better to switch. When you're given the choice to switch, it's always better. Okay, and so let's see a demo of this in running, and that will give us some insight. Why is it always better to switch? Okay, so here's our program. Let me make it bigger for everyone so everyone can see. There we go. Okay, so standard boilerplate stuff. And so what we're going to do is, so we're going to make this game. So this is kind of we're gonna kind of write this simulation. It's going to be kind of one of the more substantial programs that we're going to write and see in this course. And so first thing that we're going to do is we're gonna kind of create our data that we're going to use for the game. And so I want to create the doors. And so this will be all of the possible combinations that could be for the prizes that are behind the door. And so we're showing the car, the good prize, and there's going to be 2 goats, and we want to differentiate between the goats. And so we'll call the first goat, and then the second one, second goat. Okay, so these are all the possibilities of things that can be behind doors. And we're going to make a goat array, okay, that just has the goat and the other goat in there. And so we're going to write also, so those are our structures, right? So we have a door array that shows our 3 prizes. And then we have a goat array, which has our our two goats. And what we're gonna do is we're gonna write a helper function, okay? And so this little function here is just a little bit of code that will give us, if we pass in a goat, if we pass in either first goat or second goat, it is going to return us the other goat, okay? And we'll see in the code why that's gonna be helpful for us. But basically all it's doing is it's using an if statement that we learned about last time. And so if the goat that we passed in, right, so the a goat is our parameter that's being passed into the function, and we can use that as a name inside of our function, and that's going to have the value of whatever we call that function with. And so if a goat is equal to first goat, then we're going to return the second goat, and vice versa. If we pass in the second goat, we're going to return the first goat. Okay. And so when we write these functions, it's always good to kind of test in isolation. So let's test it to kind of make sure it does what we want. And sure enough, if we pass in the first goat, it returns the second goat. And if we pass in the second goat, it's going to return the first goat. Okay. What happens if we pass in something else that's not a goat? We get nothing back. And in particular, in Python speak, we actually get a literal called none. So if I actually take this and just actually print out the value here, you can see that it actually prints out something called none from there. But we only care about getting back the first goat or the second goat for this. Okay, so now we're going to write this Monty Hall function, and here we're gonna use random. Okay, and so if you remember how random works, if we pass in an array, and we're passing in the array of doors, and if you remember our doors as our 3 prizes, and so we're going to simulate playing kind of one round of this game. Okay, and so the contestant, let's assume that they choose randomly, and here we're using the random choice. So it's going to return one of those 3 elements in the array, and we're going to assign that that value to the contestant choice. Okay. And so once that's locked in, if the contestant chose the first goat, okay, so the door, what we're saying here is they picked a door that had the first goat behind it. Well, then what the Monty choice, that is going to be the door that the host reveals. Well, he's always going to reveal a goat. He's never going to reveal a prize. So if the contestant picked the first goat, then he's going to reveal the second goat, and then the remaining door, the door that hasn't been opened and that isn't the contestant's choice, is going to be the car. Okay, right? Because we have 3 doors and 3 prizes, so it has to be that way. And conversely, if the contestant chose the second goat, well, then Monty will open the first goat and the remaining door will be the car. And then finally, if the contestant actually picked the winning door and was a car, well, then actually in this case, Monty has a choice which door to open. Both doors have goats. And so what we're going to do here is we will just randomly pick one of the goat doors. Okay. And then the remaining door will be the other goat. That's where our helper function other goat comes in. Okay. And so then the thing that we return is we're going to return an array of these 3 things. That is going to be the data that we return in that order: the contestant choice, the choice of the door that the contestant made, the door that Monty revealed, and then the remaining door. Okay. All right. So if we do that, and now if we run this once, you can see we get back the array, and that happens to be one instance of the game. And if we run it every time, we'll get, slightly different results running it each time. Okay. And so now what we can do is we can collect that results. And we'll make that into a game. We'll make that into a table. And so what we're going to do here is first, let's create a blank table. And so we just use the table function, and then we pass in an array of our 3 column names. And so now we have a blank table. And now what we're going to do is that we're going to run the game. We're going to run the game, and so we're calling the Monty Hall function, right, which will return us an array of playing one instance of that game, and then we're going to append it to our games list. Okay. And so if we see that, if we run that table, if we run this cell, we can see our table now has one instance, right? And we can run this again and again and again and again. And each time we do that, we're going to kind of build our table, right? So we could sit here, and if we wanted, if we wanted to run this like 10,000 times, we can sit here and press the button 10,000 times. But that doesn't seem like a very good use of our time when we can have the computer do it. And that is where looping and the for loop comes in, right? So if you remember from last time, how the for loop works is for I, and so this is going to be some name that we give, and it's going to execute the body of this loop. It's going to execute this statement right here. This is known as the body of the loop. It is going to execute it one time for every item in this list. And so we're creating this range. We're creating this list that has 10,000 elements in it. And you notice in this case, right, we're looping just to run this 10,000 times. And so we don't actually care that we're running it the 5th or 6th or 7th or 1,000th time. And so we don't need to use this variable, this loop name here in our body, but it's still important that we define it. That's just Python syntax. And so this will run 10,000 times, and it'll create us a table for us. So if we run that, takes a few moments to run, but then there's our table from there. Okay, so now we've kind of simulated playing 10,000 10,000 instances of that game. Okay, so now we can actually collect some statistics. Okay, and so what we're going to do is we're going to use the group function. So, right, the guess column, if you remember, is that is what the contestant guessed. Okay, and so if we group by the guess, it's going to show us our 3 categories of guesses, right? Whether we guessed the door that had the first goat, the car, or the second goat. And so if we group that, then we can get, remember, the default to group is going to give us a count. Okay, and you can see that, and this is not terribly surprising, right? We ran this thing 10,000 times, and you can see roughly about a third of the time we picked the car, about a third of the time we picked the first goat, and about a third of the time we picked the second goat. And this all kind of makes sense from probability, right? If the guess was random and the prizes were distributed randomly around the door, behind the doors. If you pick one door, you're gonna win the car 1/3 of the time. You're gonna get the first goat 1/3 of the time, and you're gonna get the second goat 1/3 of the time. Okay, and so that is the probability if you played the game, you picked the door, and you didn't change your choice. You just stayed with it. Do you believe me? And I'm not doing anything like, does that make sense? And the reason why I'm asking that is that this has been quite controversial. And so I want to make sure we got kind of buy-in that makes sense. Right? If we picked our door, and then Monty revealed another door, and we stayed with our choice, we're going to win the car 1/3 of the time. That's not controversial, right, to any of us? Awesome. Okay. So now we can calculate the probability of, right, we see the counts, but we can actually, we can just, with just a little bit more math, we can actually calculate the probabilities. And so here all we're doing is we're taking the counts, from the stay table, and we're just taking the count for each particular item, for item 0, and then which is the car, and then dividing it over the sum of the counts, right? So if we just run that, we can see that the probability of winning the car is about 0.33, about 33% from this, simulation from there. Okay, and that's not controversial. But so now then the question is, so what if you made the choice? If you made the choice to switch, when Monty gave you the choice, do you want to switch doors, right? So you're going to go from, if you look at the table, right? This is the guess. So this is what you had. This is what we revealed, and we made the switch. When we make the switch, our choice is now coming from this remaining column. It is now coming from the third column if we made the switch. Okay. And so we can do the same statistics. So if we made the switch, how many times was the car? You know, we can get a count of how many times a car was there and how many times a goat was there. And if we do that, now we can look on the remaining door. In the remaining door, the car was there about 2/3 of the time. And the first goat and second goats are about 1/6 of the time from there, right? And so, you know, if we do the counts again, if you switched, you're gonna win about 67% of the time if you switched, right? And so, you know, where does this come from? Yeah, Juliana.
You can finish. I had a question from before.
The big reveal is that, you know, the way you think about it is that once you've made that choice, the initial choice, right? The way the game is played is that if you guessed right, 1/3 of the time, you're going to win the car. And then, you know, if you think about the choice of either winning or losing, you know, as being the two distinct choice, if you switched, you're going to get 1 minus 1/3, right? If you didn't switch, you're going to win the car 1/3 of the time. If you switched, because those were the only two possible outcomes, you either won the car or you didn't win the car, if you kind of frame it that way. If you switched, your probability of winning is going to be 1 minus 1/3, or 0.666% from there, right? So that's kind of like the probability. But, you know, notice, you know, what we did was we didn't actually have to kind of figure out any of the probabilities. We just ran an experiment. We ran a simulation. And as we'll find out kind of from today's lecture, as the number of times you run the simulation, as the data grows, the more likely that the results will converge to the actual probability distribution. Okay. Yes, Juliana.
I had a question about the I. I just wanted you to.
Oh, absolutely. Yeah.
So why is it there again? It's just standard syntax.
So the way the for loop works, so the answer is for this example, it has to be there because of the syntax of Python. So this is how the for statement works. It is the keyword for, and this is known as, in computer science speak, this is known as the loop variable, but variables in this course has a very specific meaning. A variable is actually the attribute of a column. So we don't use the word variable in this course. So it is the loop. And so I slip up because I'm a computer scientist. So you probably hear me say variable and I correct myself and I say name. we call these things names, you know, in this course. So I is a loop name. And the way, and thank you for asking this question, because I think it's worth spending a little bit of time kind of reviewing how the for loop works. And so the for loop is a way of iterating over a list, okay? And so let me say that again. So the for loop is a way of performing some computation over every item in a list. And we've done this before, right? We've done this before with arrays. But this has all happened kind of behind the scene, right? With like the apply method. Behind the scenes, it is kind of doing the code that we are kind of talking about now. And so specifically what happens is, so the syntax of a for loop is the keyword for, so that is the keyword, and then it is some loop name, and that is any name that we want to give. And then it's the keyword in. And then this is something that evaluates to an array. Okay, in Python speak, it's a list, where we're kind of using arrays and lists interchangeably in this course. So this part here is anything that evaluates to an array. And then we have the key, and then we have the colon, which is part of the syntax. And then this is known as the loop body. These are all of the statements that are going to get executed once for every iteration of the loop. And so how it works is, it's going to take this array, and whatever the first element of that array is, and in this case, because we're using the range, this list is going to have the values 0 through 9,999, because the default for range is it starts 0, goes up to, but not including the endpoint. So there's going to be 10,000 items in this list, and it's going to start at 0. So what's going to happen is that Python is going to assign the name I to have the value 0, and it is going to execute the body of this loop. Because we're just using this as literally as a counter, as just to say, hey, execute this statement 10,000 times. We don't need the name of this. We don't need the name of all of the items in this list. But you can imagine a scenario. Imagine where that list was an array of names, okay? And you wanted to do something with those names. Then you would actually use the loop name from there. Does that kind of answer your question? Awesome. Okay, great.
Thank you.
Okay. So we could spend an entire course on probability, and as a matter of fact, the math department has entire courses on probability. We are going to get the super crash course in probability. This will be just enough probability for us to kind of run our simulations. Okay, so I don't want to pretend that we are now going to become probability experts, you know, from the next few slides, but this is just kind of enough that we can be kind of dangerous and run our experiments. And so very, very briefly, we can think of probabilities as having the numeric values from 0 to 1, and we can express those as percents. So the lowest, and when we think about the probability, we talk about the chance of some event happening or not. And so the lowest value would be 0 or 0%. And 0 would represent that is impossible. The chance of that event happening is non-existent. We can, you know, play that thing a million billion times for the end of times, and that outcome would never happen. Firstly, the highest value we can say is 1 or 100%. And that means the chance of that event is certain. Okay, so basically what that means in terms of kind of events, right, is that if an event, you know, in our definition is either going to happen or not. And so if an event has a 70% chance of happening, then the chance of it not happening, because it has to add up to 1, the chance of the item is not happening is going to be 100%. Minus 70 or 30%. Okay, so the sum kind of your probabilities need to sum up to 1 or 100%. Okay, so there's a couple of scenarios that are worth kind of talking about, and one which happens kind of fairly frequently is this idea of events having equally likely outcomes. Okay, and so if we have an event that has equally likely outcomes, and you know, the canonical example is thinking about flipping a coin, flipping a fair coin, rolling a dice, right? Assuming that the dice is not a loaded dice and the coin is fair, all outcomes are equally likely, right? And so to calculate the probability is that you can take the number of outcomes that make the event A happen. And so for a dice example, it could be what's the odds, or what's the probability of rolling an even number, okay? And so we would just count out the total number of outcomes. If we just think of a standard 6-sided die, the total number of outcomes is going to be 6. And then the number of outcomes that make it happen, you know, 2, 4, and 6, right? So we just basically take the number of outcomes that make it happen, 3 divided by the total number of outcomes, and then you can see the chance of rolling an even number is going to be 0.5 or 50%. Okay, so that's kind of what we do when they're all of the events are equally likely. Okay, so we also want to talk about the multiplication rule, and this happens when you have 2 events. Let's call them A and B, and we want to kind of get the probability that both A and B both happen, right? The key word here is A and B. And so when we have that scenario where we have 2 things that are going to happen, the multiplication rule comes into effect. And so what that means is to calculate the probability that both A and B happen, one way to calculate the probability is that you calculate the probability that A happens, okay? So we calculate the probability that A happens, and that's going to be some probability between 0 and 1. And then we're going to multiply that by the probability that B happens, but, and this is important, we're gonna do this probability of that B happens given that A has already happened, okay? And the reason why we're doing that is because we're basically calculating the probability that both A and B happened. So for A and B to both happen, A will have had to have happened. Okay, so if we calculate the probability that A happened and then the probability of B given A, that, and we multiply the two of them together, that will give us the probability that both A and B happen together. And so kind of one insight you can kind of glean from that is because probabilities all go between 0 and 1, and we're multiplying together, we're multiplying these two probabilities together, well, the answer is going to always be less than or equal to the chances of each of the individual probabilities of being have happened, okay, you know, individually. And so the idea here is you have more and more events that all have to happen. The probability that all of the events will happen is going to, it will become less likely to satisfy them all, okay? And you can do this for, you know, for more than just A and B as well. You know, if A happens and then calculated that B, given that A happens, then C, given that A and B happened, and so on and so forth from there, okay? So when we have this condition where two events both have to happen, the and, we're going to use the multiplication rule. Conversely, we can look at events where we want to say an event can happen in exactly one of two ways. So if we have, basically what we're saying is that an event can be satisfied by P the first way or P the second way, okay? So if we have two ways to kind of satisfy an event, this is really, we're getting to an or situation. You know, and so like kind of an example, let's see, so you could say, I pull a card from a deck of cards, and the event could be whether I get a heart or a club, okay? So there's two ways to kind of satisfy that event. The probability that you get a heart or the probability that you get a club. And so we have this or, and so this is where the addition rule comes in. And this is where you're going to add the probability of the event happening in the first way to the way that it could happen in the second way. And conversely, because now we're adding together, the probability that you're going to get is going to be equal to, greater than or equal to, the chance of each individual way. And this makes sense, right? Because of this or. You're giving yourself more opportunities to kind of satisfy the event from there. And so the way I kind of remember it is that when you think and, it's multiplying. When you think or, it's going to be addition. And so it becomes harder when you string to get events together, A and B and C. The probability of all of them being satisfied is either, you know, tends to go down, and then or, you're doing addition, so the probabilities are going to become more likely from that. Okay, so let's look at a couple of examples. One, let's think of a coin flip, and so let's calculate the probability of at least getting one head for a certain number of coin flips. So if we toss a coin 3 times, at least one head is any outcome except for the 3 flips that give us tail, tail, tail. And so when calculating these probabilities, you know, we actually kind of have a choice, right? We can calculate the probability of at least one head, but sometimes it's actually easier to kind of calculate the probability of the not outcome, right? In this case is, what is the probability that we get all tails? And if we compute that, then we know the probability of at least one head is just simply going to be 1 minus that probability. from there. So in this case, it's actually easier to just calculate the outcome of tails, 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 and then the probability is going to be 1 minus that. So what does that look like? Well, if you think about it in terms of each of these trials are independent, and so each coin flip, and so the outcome of tails, 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 right? Getting a tail for the first flip is 50%, and so that's our outcome. And then the second trial, again, we have a 50% chance of getting a tail. So that's where the second half comes in. And the third trial, we have a 50% chance of getting a tail, right? And so, you know, calculating the probability of getting a T and a T and a T, right? We hear the and, so we're gonna use the multiplication rule. And so we're gonna get a half times a half times a half, which is gonna give us 1/8. And then the outcome that we want, at least one head, is 1 minus that from there, or about 87.5% of there, okay? And we can do that for any number of tosses. 10 number of tosses is the same thing, except for instead of doing this 1/2 times 1/2 3 times, we're gonna do that 10 times. And I've just shown that here in Python notation. This is the equivalent of taking 1/2 and raising it to the power of 10. So that's the same thing of saying 0.5 times 0.5 times 0.5, you know, 10 times. And if we do that math, we put that through, we find out 99.9% of the time, right? It is extremely likely that you would get at least one head from there. Any questions about that? Okay, great, awesome. All right, so let's have a discussion question. And so kind of to put our newfound probability to the test. And so we have a population, has 100 people, okay, including Mo and Joe. And so one question is, so what we're gonna do is we're gonna sample 2 people at random without replacement, okay? And so again, sampling without replacement, you know, I always think of picking names out of a hat, right? So we have 100 names in the hat, we're gonna pick one name out, and then we're gonna pick the next name without putting the first name back in. So that's sampling without replacement. If we sampled with replacement, we would pick a name out of the hat, look at it, record that value, and then put it back in. Put it back in the hat, shuffle, do that again. But we're picking without replacement. So once we've picked out a name, it stays out of the hat. So now the question is, what is the probability of both Mo and Joe are in the sample? Okay, let's go into breakout rooms. So if we take a look, and there's actually a couple of ways that we can calculate that. One way to calculate this is that first, the probability that the first sample picks Mo and then Joe, or, right, there's 2 ways to kind of satisfy this event, right? That first we pick Mo, then we pick Joe, or first we pick Joe, then we pick Mo from there, right? And so what is that probability? The probability that we first pick Mo is, well, there's 100 people in there. Mo is one of those 100. So the probability that we pick Mo is going to be 1/100, right? And we're sampling without replacement. So then the question is, what is the probability that we pick Joe? Well, Joe is still in that population because we picked Mo first, right? And the probability we're calculating is, you know, that we picked Mo, given that we first, you know, we picked Joe, given that we first picked Mo. So there's not now, instead of 100 people in the room, there's 99. And so the probability of picking Joe is 1/99. So that is the probability of first we pick Mo, then we pick Joe. But that is only half of the possible conditions. The other possible way of thinking about that is that first we pick Joe, then we pick Mo, okay? And then that's the same kind of logic from there. 100, you know, 1/100 times 1/99, and that gives us 0.0002%. Another way that we can think about it is that Actually, I like kind of explaining it that way. Did anyone come up with a different way of kind of reasoning through it? No. Okay. Awesome. All right. So that is kind of that is an example of kind of using kind of the OR rule. And then let's take a look at another variation of that. What about calculating that neither Mo nor Joe is in the sample? And so I'll send you back over to the breakout rooms. Okay, so to calculate that, we want to again look at this as kind of two samples. And so the first sample, the first person we pick out of the room.
Sometimes they are on that, like in the middle.
You say again?
Class they had the intern on there, but can't expect that from everybody.
Were you asking someone asking a question? So to calculate if neither is in the sample, we have to look at the first pick. And so what are the percentage of that neither Mo or Joe is in the first sample? Well, they're two members of the population. So 98 out of 100 would be for the first selection, right? So those are all the possible ways of picking someone from the room that's neither Mo nor Joe. You're picking 98 out of the 100 people from there. Okay, and since we're sampling without replacement, then the question is for the second sample, right? We've already drawn one out, so the total population is now 99, and we want all the possible combinations that are not Mo or Joe, and we have 97 of those. And so since we have an and situation, we're going to use the multiply rule. So we're going to take 98 over divided by 100, multiply it by 97 over 99, and then we get 0.9602. Does anyone have any questions on how I got that number? And did it match yours? Awesome. Good. All right, so we'll come back to kind of this idea of probability throughout the course, but that's kind of the basic groundwork that we'll need to kind of start running and doing our simulations.